Welcome to day 2 of our MVM MPH workshop. Glad to see all the smiling and bright faces this morning. A variety of things happening today, a bit out of the ordinary. Let me put that up where you can hear me. On the first slot this morning, Roger Morris has come back with us to give some of his wisdom about disease control programs and other topics. We'll move into a break, and then we've got some media activities happening mid-morning. So when we get done with Roger's talk, I'll try to bring some more detail to that before we turn you loose so you have some sense of what's happening. And then we move on with some workshops and breakout sessions for the rest of the day. So Roger's talk this morning, evaluation of disease control programs and especially zoonoses. I gave a bit of an introduction to Roger yesterday, so I won't dwell on that at great length this morning. But I think you'll find Roger's a really great storyteller, and if you pay attention, you might even learn a couple of things, and there might be a few nuggets of wisdom in there. I've been around this game for a long time, and I never fail to pick up on something when I listen to one of his talks. So sit back and enjoy it. Roger, the podium's yours.
Right, thank you, Eric. So I better work out how to organise this thing. Yep, no, I've got it. Yeah. I've handed out to you the key slides. So I'm going to talk to you about all the different steps in evaluation of disease control programs, with particular reference to zoonoses this morning. And basically this is a framework for the rest of the 2 weeks. So in order to fit this into the available time, I'm going to just cover the high points, but what you've got in front of you is the framework, and during the rest of the 2 weeks you'll have a series of other talks which fill in each of the components of the process. In order to make this more interesting, I'm going to use avian influenza as my case study examples all through the talk, and outline to you some examples of how these different techniques have been used for avian influenza. And then you'll go on later in the morning to the case study that you've got in front of you, and I'll explain that a little bit later. So what I want to show you this morning are the steps for evaluation of any planned disease control activity, and prepare you for the sessions that we're going to have. These are the steps that we're going to work through. I'm going to skip step 1, the evaluation of priorities for action, because that's a big topic in itself, and we're going to focus on specifically how you operate disease control programs today. Then we're going to look at how you evaluate control options for the disease that you've decided is your priority, and each of your groups has now decided which disease you're going to work on over the next 2 weeks. Briefly touch on evaluation of benefits and costs. I am actually trained as an economist as well as a veterinarian, and I'm going to be organising the MVM economics paper a little later in your program, so I'll just lightly touch on that. Looking at risks in programs, what are the weaknesses and risks that you need to deal with? How do you evaluate progress of your control program? And how do you assess the outcome several years down the road and determine what lessons you've learned? Now, there's a wide range of disease control situations that we deal with, and this is just a summary of them, but they all basically are just variations on the same theme, and the principles that I'm going to take you through this morning apply to all of them. We'll talk about how you manage an endemic zoonosis to reduce the prevalence in both animals and man, using avian influenza as it's become established in Asia. Now, step number 1 is the epidemiological evaluation of the situation. We want to firstly understand the transmission routes by which the disease is spread between animals and between animals and man. And we want to, if possible, quantify them to decide which ones are most important and which ones are relatively minor. And also, what are the shifts going to be as we undertake our control program. Most diseases spread by more than one transmission pathway, and quite often our disease control programs focus on the most important pathways. As the disease is reduced, then what was previously a minor pathway that we didn't worry about at all can become the most important pathway of transmission of the disease. So we've got to adjust our control strategy as the program goes on. The next issue is what's the role of different species in multi-species diseases such as zoonoses? What are the reservoir hosts, the species in which the disease is maintained in the long term? What are the short-term maintenance hosts to which disease is transmitted, but they then maintain the disease as long as you don't carry out control measures? What are the spillover hosts, the ones that are not normally significant in the disease, but if there's a lot of infection around, will get infected, but are usually fairly minor in the epidemiology of the disease? And what are dead-end hosts that get infected but don't transmit the disease onwards? So worrying about them in a control program is really a waste of time. Now, this is one issue that we've battled around a lot in New Zealand in relation to bovine tuberculosis. There are 15 species in New Zealand which can get infected with bovine tuberculosis. If we controlled all of them, then we would never be very effective in our control strategy. But a number of them are actually dead-end hosts. They can get infected, but they don't transmit effectively. And for example, a wild pig is not a significant host for transmitting the disease onwards, even though infection can be reasonably common in the wild pig. An animal called the stoat, which we foolishly imported from Britain 100 or so years ago, can get infected, but it's a spillover host. Infection dies out naturally even if you don't control it. And that's a species that we fought bitterly over for several years. Is it important? Is it not important? And the answer came down to doing some good epidemiology and showing that no, it wasn't important. And then we have the possum. That is the main, this is an Australian imported animal that is the main species that transmits the disease in New Zealand to cattle and deer and other animals. But it got infected probably from deer, which are the underlying host, not very important in the disease, but if you eliminate it from possum populations, they're at risk of getting reinfected from deer populations. So you've got to weigh up which species you're going to focus on and how you're going to do it. And that's true of most diseases. Now then, what control measures are feasible, what are preferred, and what surveillance measures do we need? The first thing is to work out what are the risk areas. And this is a map of Bhutan. Mark Stevenson, one of the people you'll meet over the next couple of weeks, did some work in Bhutan looking at all the different factors that needed to be taken into account and then drawing up, using quantitative epidemiological methods, a risk map of where avian influenza was likely to occur. He did this in 2009, and Bhutan had got by for many years without any outbreaks of avian influenza, and they were a bit confident that they weren't going to get it. But then, in February 2010, they got an outbreak right bang in one of the high-risk areas that the group had worked out using epidemiological analysis methods. Now, prior to that, as a first part of that particular exercise, the people sat round as a group and did a qualitative assessment. Where do we think the disease will occur? And there, they covered 2/3 of the country. Now, if you consider a very large area that's at high risk, then you're spreading your control effort wide. Whereas if you focus in on doing a proper epidemiological analysis, then you can concentrate your efforts in a more limited area. So we try to not just think about the issues, we try to quantify them and measure them. We we need to know the prevalence of a disease in each of the at-risk species, the variation by geographical area, by subpopulations of both people and animals, and by particular risk groups. If we're planning a control program, we need to at least consider both the incidence and the duration of disease, because those two factors determine the prevalence. If you want to reduce a disease quickly, you have to reduce the duration of disease, how long animals are infected, as well as the incidence, the new rate at which animals become infected. If you just reduce incidence, you slowly reduce the disease. If you reduce both incidence and duration, then you reduce it far more rapidly and get better results from your control strategy. So you need to be thinking about that in relation to how you design your control program. Reducing duration in animals we often do by slaughtering them, right? The infected animals get killed and you have a dramatic reduction in the number of infected animals. That's reducing duration. Tough to do in people, but in people we can treat, for example, as a way of reducing duration. Oh, why is it not moving forward? Whoops. Sorry. Right. Right. We're back to the... No, I don't want to go too far. That's... Well, now I've got one. So if I do right arrow, this one,
sticky slide there. Maybe with the presentation itself.
Sorry, that doesn't seem to want to move on. Next one.
Yeah, it doesn't let it slide for some reason.
It's not a particular. I use the slide constantly. Right. Let's try that. Oops.
Oh, wait, still, yeah, no, still beginning there.
Macintosh. Right. We're back on. So this is seems a bit distorted. This is looking at the human cases of avian influenza. This is planning out control strategies, looking at distribution of cases. Human cases, poultry cases of avian influenza in Vietnam. Heavy concentration of poultry cases in the Red River Delta and the Mekong River Delta, right? And limited numbers in between, but this is actually an area where there's a lot of trucks and things stop over when they're moving between the high population areas, and we think that might be a factor in this cluster in the middle. And you can see that there's a nice match between the distribution of the human cases and the distribution of the poultry cases. The same in time. This is the... Oh, we're not doing very well. For some reason, the poultry cases are not showing up, but this is the human cases in the top, and in time they're matched with the poultry cases. When the poultry outbreaks occur is when we get the human cases. Now, the situation in Vietnam, control is by vaccination and local stamping out at a very localised level. The outbreak numbers in Vietnam were very high in the early stages of the epidemic. They've been reduced, but there are still outbreaks going on. There are outbreaks going on right at the moment. In Vietnam, the duck is the main infected species. Chickens are exposed, but interestingly, we're doing a longitudinal study in Vietnam, and to my personal surprise, we're getting very little transmission across to chickens, even though they're living in the same environment as the ducks. In other countries, that doesn't seem to be the case. One of the things we're finding is significant subclinical duck infections. Not all of the infections are causing clinical disease, but when we investigate the virus, we find that it's the same highly pathogenic H5N1, and yet in some cases it's causing disease in ducks, in other cases it's not. When we look at risk factors, we find that village factors are not strong risks, somewhat surprisingly, and it seems to be household behaviour, the way individual people look after their ducks, market their ducks, buy in ducks, move the ducks around, that are the risk factors for the disease. Now, China is an interesting contrast for evaluating the disease situation. They have a national mass vaccination program, and they stamp out for 3 kilometres around case flocks. But whereas in Vietnam there's a strong association between human cases and poultry cases, in China that's simply not the case. The human cases and the poultry cases are widespread around the country, and they occur in different areas. There's a surprisingly small number of poultry cases in relation to the number and the location of the human cases. This is a quick summary of the human cases, and there's just been one recent one in Hong Kong where the person appears to have been exposed in China, but yet there's been no poultry cases in 2009 or 2010. But when we look epidemiologically at this, there's been a case control study showing that if for cases, if they've had contact with sick or dead poultry, their odds ratio is 507. Now, you all know about odds ratios. That's a remarkably high odds ratio. Even just indirect contact with sick or dead poultry, it's got an odds ratio of 57, and simply visiting a live poultry market has got an odds ratio of 16. So we've got the typical risk factors present, but we don't have cases being reported in poultry. But when you go out and measure the virological prevalence using PCR, we find that across the provinces over 3 years that have been studied, we have no infection in the industry flocks at all. But we have a lot of infection in backyard flocks. We have a lot of infection in live bird markets and slaughterhouses. And interestingly, we have very little difference really between ducks and chickens in China. So some epidemiological differences, which I'm not going to try and explain. I have my own views on what the explanations are, but this is exactly the kind of thing that you should be looking at in a control program, to ask the question, what do we need to do about this disease? And my answers are different for China and Vietnam, both of which I'm involved in. Now, this is just a list of control options. It's not a complete list, but it tries to identify the different things that you can do to control the disease. We then formulate alternative control policies, and my general view is to formulate, say, at least 3 different possible control policies, and then to evaluate them in order to provide advice. If you just look at one control policy and tell the government what to do, they're not really getting an idea of what the options are. And typically we're not just looking at do we vaccinate or not vaccinate or something like that. We're looking at the scale of expenditure, the timing of how you do things. And normally what I do at this stage is to make a quick guesstimate of what I think the effect will be, and then go out and look at the scientific literature, look at the available evidence, and refine the estimates. We use a technique called computer modelling to model disease control. We're using this in a number of countries, as I'll show you in a moment, where we have a computer model that lets us model any infectious disease in any country. All we need is the geography of the country and the production system, and we can do an evaluation. This often answers questions that are very difficult to answer by other methods. Another valuable technique is using pilot trials to test the feasibility and the likely costs and benefits of larger scale control. Now, this is an evaluation we did for Britain of avian influenza control policies. So on the left of each of these is no control. On the second line is vaccination only. The third is vaccination with depopulation, and then depopulation only. And we've looked at an expected size incursion of avian influenza and a high level incursion of avian influenza. And this particular one is with disease getting into free range flocks. Now, we don't get big epidemics, and that's exactly what Britain's found. It's actually now, this was done several years ago, it's now had some incursions, and it hasn't had widespread of the disease as we've seen in Asia. But this lets us look at the range of expected outcomes, the effect of severity if we have more incursions or more initial outbreaks is what this represents. Then we get a bigger outbreak, but still a manageable size outbreak. So this is quite easy to do using this computer modelling technique. It takes time and effort, but we can do it even with fairly limited data. This is doing the same kind of modelling process in Vietnam, looking in the Mekong River Delta at without vaccination and with vaccination the number of outbreaks. You can see that vaccination reduces the problem, but it certainly doesn't eliminate that, which is what's been found. And in fact, if I look at the Asian situation, the countries which have not vaccinated have been much more successful in controlling the disease than the countries which have vaccinated. Socio-economic evaluation. We need to look at who gets the benefits and who pays the costs of the control program. Economists look at something too called externalities, where if I fail to control the disease in my flock, then my neighbours suffer as well as me. In some diseases, I keep the costs and the benefits inside my flock. In other situations, I can't. Now, the large commercial producers can keep the benefits and the costs inside their flock. The village people cannot. And so this is one strong reason for government investment, because of what we call the external benefits and costs. If we've already decided what we want to do, we can do a simple thing called cost effectiveness analysis, decide what's the best way of reducing this particular disease. That's a simple thing to do. Or we can do a more complex benefit cost analysis if we want to see what the payoff is for the resources we would invest in the control program. Now, we're not looking just at the overall benefit cost ratio. We want to look at what's the ratio for public funds, what's the effect for different size smallholders and large flocks, what's the benefit for people who simply buy chickens, for example, because there's another externality. I just go to buy a chicken at the market and I die of avian influenza. So we need to look at all these components, and I can't deal with it in more detail. This is an analysis by the World Bank just showing what would be the effect of different sizes of flu pandemics, which was done before the H1N1. And South Asia, in this analysis, is relatively, it's not far from the highest affected region of the world, but it does depend a bit on the outbreak, but it certainly would have very severe effects. And in the 1918-19 epidemic, your region of the world was very severely affected, right? But the counts that are normally given for the deaths from the 1918 infection did not include your region of the world because no one was counting at that stage, and so we think probably something like half the deaths occurred in South Asia at that particular time. So influenza is an important disease from your point of view. When we're doing benefits and costs, cost assessment, it's much easier to estimate the costs than the benefits. We're only concerned with the variable costs. In other words, we don't have to worry about the government salaries of people who will be employed anyway. We have to worry what are the additional investments we're going to make and what are the benefits that you will get from that. The benefits to the animal owners are relatively straightforward. There's some challenges, but we can measure the effect of changes in productivity, changes in death rates and things like that in chickens or ducks, and we use what we call representative sets of owners to make this assessment, different scales of production. More difficult to estimate the benefit to people, and the technique that's commonly used is something called disability adjusted life years. What's the effect on the population life expectancy of a particular disease, adjusting for the fact that the disease may not kill you, but you may have a much less satisfactory lifestyle, which is why we use this disability adjusted factor. I don't have time to go into any more detail on the economics, but it's an important part of any analysis. Another important issue is whether the program will gain support from different parts of the community. And we need to assess community attitudes as part of this assessment. Are people aware of the disease and therefore know what they should be doing about it? Are they motivated to participate according to which at-risk group they're in? And are the funding sources and the delivery agencies supportive of controlling this disease? Now, the studies that have been done, there's been a number of economic studies of, and community attitude studies of avian influenza in Asia. In general, governments and large poultry producers in Asia are strongly motivated to control avian influenza because it causes them problems. But smallholders are motivated to avoid reporting disease because it has a negative effect on their short-term income and on their credit position. And so there are lots of examples in Asia of suppression of information about outbreaks of avian influenza because it's not in the not in the interests of precisely the populations that are affected to report the disease. A very important factor as to why we get these unexplained issues in avian influenza control. So we need surveillance systems which don't just deal with reported disease but also detect infection. Now we need to decide for our control program how we'll manage it, commonly called the governance nowadays. What's the role of government, of different kinds of animal owners? What's the role of industry associations and cooperatives? All of that needs to be dealt with in planning the program. Our operational arrangements, we need to get a clear objective for our control program. Far too often we just say we want to control this disease, but it's never that simple. You need to define the objectives in much clearer terms, then formulate an integrated control strategy that is designed to achieve those objectives, work out how you're going to implement it progressively, both in time and in geographical areas and in production systems, and consider whether you want to use a pilot phase to test feasibility. Then a crucially important part is assessing program achievements. as we implement the strategy, we've got to have monitoring and surveillance systems to measure our outcomes in relation to the objective. And I like to divide the into two kinds. Performance indicators that give us an overall assessment of how good progress we're making towards our objective, and then diagnostic indicators which measure deviation from the epidemiological pattern we're expecting to find as we control the disease, and tell us why we're getting certain undesirable trends in the course of the program. For example, one simple illustration of this is we've got a program to control the disease. It's reducing the number of infected herds, but if we've got an excessive number of negative herds that are becoming infected, then our program is not going to work. And uninfected herds getting infected is a very good diagnostic indicator to tell us whether our spread control is working effectively. Just one simple example. This is just some illustrations of techniques that can be used to monitor disease. This is something called the estimated dissemination rate. I'm not sure whether you've met this yet, but this is avian influenza in Vietnam, and this basically tells us about 1 to 2 weeks ahead what we can expect to be the trend of the epidemic. We should see a pattern like this. The red line is showing us, because I've now got the actual epidemic, the red line is predicting that we're going to have cases. If the red line comes above this value of 1, the disease is spreading. Only when we get it below 1, the disease starts contracting. Now, this is doing exactly what we think the estimated dissemination rate should do. In this one, I think we're missing a lot of cases because the epidemic is rising before the dissemination rate is rising, suggesting that there are quite a lot of cases that were not being detected at this earlier stage of the outbreak. So this is the kind of thing in avian influenza where you've got to move quickly, being able to analyse this and say 2 weeks ahead, red alert, we're going to have problems, or calm down, Minister, the outbreak is easing off. That's a really important kind of diagnostic technique to use. We can look at things geographically also. This is showing the distribution of poultry household density, showing us that this is the most dense area in the Mekong, but our outbreaks don't lie in the same place. We've got outbreaks up here where the poultry density is much lower. There's something going on up here that we need to investigate to find out why we've got outbreaks in that area. In understanding disease spread, we can use a technique called social network analysis. And this is a particular example from Bali, looking at the movement of poultry to live bird markets and the risks, therefore, that are associated with this of spread of avian influenza. If you want to understand the role of markets in disease, you need to do social network analysis to find out just where the birds are moving and how that influences the spread. And this is a very useful technique to understand disease spread patterns, particularly when you're looking at a market spread disease. Now, we need to discriminate in dealing with a control program. I'm not doing too badly for time. Between changes that we expect as a control program progresses and changes that are abnormal. And we constantly have this issue of people talking about false positive tests and complaining, particularly as a control program progresses. They say, but you're killing far too many of my not infected animals in my herd. You killed these animals and then they didn't have disease. This is a direct consequence of epidemiology, because if we take a very good test, I just want to make this general point to you because it comes up so often. that's a very good test, 95% sensitivity, 90% specificity. When the disease is common, let's say 30% prevalence, then we get a predictive value of a positive test of 80%. And I'm sure you are now really knowledgeable on predictive values. So, and 98% for a negative test. So we're not going to find too many false positives here, are we? But when the prevalence is 3%, our positive predictive value is only 23%. We've got a 99.8% predictive value for a negative test, but we're going to get far more false positives, no matter what the test. It doesn't. People say the test's not doing well. The test's doing just as well as it always was, but we're working in a much lower prevalence population. So we have to use epidemiological investigation techniques to then investigate these false positives in the late stage of the program. The other thing is that as you progress in a program, finding each additional case of disease becomes more difficult and expensive. And this is usually the stage at which the minister starts to get edgy and say, look, this program's costing us $20 million, but you only found 50 new cases this year, and 5 years ago you were finding 5,000 cases. What's going wrong? The answer, of course, is that it's going very right. But you have to deal with this kind of problem through the course of a program. It's also quite common at this stage of controlling a disease to find that some either host species or transmission route that seemed unimportant and you didn't worry about early in the program becomes important as the disease was is brought under control, because it represented 2% or 5% of the spread. When you had 100% of spread, it didn't matter. But when you're down to 8% of spread, then something that's responsible for 5% suddenly is the dominant method of transmission. So we need to be thinking about that in the course of adjusting the control strategy. And one of the ways we do this is to look at regions and herd types and other group subpopulations that have got slow progress. That's one of the ways we can tell what's going wrong. And this is just another avian influenza example of some of the things that can go wrong and how a little bit of epidemiology can be very diagnostic. Vietnam's a lovely case study because we've got two river deltas, both of which have had outbreaks, and so we can compare between the two. Now, this is the Red River Delta in the north, and this is the series of outbreaks. And we can see that for the first 2 years, most of the outbreaks occurred in the short period before Vietnamese New Year, called the Tet Festival. There are a number of reasons responsible for that, and clearly that's epidemiologically significant. But in the third year of the epidemic, the outbreaks occurred several months ahead of that. Initially, that doesn't make sense. But in fact, what was happening was that this was the start of the national vaccination program. In the Red River Delta, the way they ran the vaccination program is that they brought all the birds from each village together in one place and vaccinated them all together. And actually what they did was to precipitate quite a nice little epidemic of disease, right? But by then they'd vaccinated the population, they had a good immune population, and so they didn't have an outbreak at Tet Festival, right? And the same the next year, they didn't have an outbreak at Tet Festival, but now there's a new strain of virus came into the country, still H5N1, but a different variant. The vaccine was not highly protective, and so we get another outbreak, right? You've got to understand the epidemiology to know what's going on. Now in the south, in the Mekong Delta, bigger outbreaks, again, beautifully synchronised with Tet Festival, but almost no outbreaks at the time of vaccination, because there they went from household to household and vaccinated the birds within the household, and they got almost no spread associated with the vaccination program. And no outbreaks at the time of Tet Festival, but again, a new strain coming in, and they had to adjust the vaccine to take account of this. They needed to know that this was going on in order to do it. So a little simple epidemiology can solve lots of problems. This is a slightly fancy technique that we use called spatial autocorrelation. Early in the epidemic, basically what this shows is that the spread was local in nature, and it was from household to household. But, which is why we get this high curve here. But after that, we don't get evidence of localised spread, and we think market movements and people buying and selling birds and people moving birds around in somewhat larger areas became the dominant way in which the disease spread. So it changed quite rapidly once people recognised that your neighbours were at risk. That pattern disappeared and a different pattern of transmission became dominant. Intriguingly, in Vietnam, we have some areas, the brighter the colour, the very bright coloured ones have outbreaks every year. These are these are communes. They're groups of about 15 villages, and every year some of these communes get outbreaks, and every year some of these are all communes too, never had an outbreak. And we have some that have outbreaks only in 1 year, the yellow ones, and you can see that they're in clusters. Sadly, we still don't know the answer to why exactly this is going on. We're still doing investigations to try and sort it out. It's a fairly challenging problem, but we're pretty sure it's associated with the way people are managing their poultry in these different areas. But pinning down the exact cause is proving challenging. Now, we've also got to look at additional risk factors. So here, this is wild birds, and this is tracking birds by satellite mapping. It doesn't come out all that well, but here's Mongolia, where I'm involved in working on wild bird infection, and you can see we've got a flyway that takes you right down into your part of the world. This is where they breed, and very wisely they spend their winters down with you, and can carry infection down there. So while we don't want to overemphasise wild bird infection, because that does, it's probably only a very small proportion of outbreaks are caused by wild birds, but when the infection gets into a new area, that's one of the mechanisms by which it gets into new areas. So we need to understand the role of wild birds. So then we get to late in our control program, and we need to decide what lessons we've learnt from things. We want to look at some of the unexpected findings, some of the differences between subpopulations, and try and find out what it is that's causing variation in the success of our control strategy. Quite frankly, if you don't find anything that's going wrong, if you don't find differences between different groups, then you don't have a good surveillance system. Right? Wherever I see people say, no, everything's going fairly normally, we don't have any problem areas, or we don't have any problem production systems, my answer is you're not doing proper surveillance. Right? But one of the hardest things is to differentiate true epidemiological weaknesses or gaps from management faults. And quite often an area effect will be due to differences in energy and enthusiasm between the people working in that area. And in some areas, there are some countries, which I better not name, where when they have outbreaks of disease, there are little islands with no outbreaks at all and surrounded by outbreaks. My first question is the person in that area hiding the disease? And mostly that's the first explanation. The second explanation is they're not making enough effort to find the disease. The third explanation is that they're doing a much better job than their neighbours, right? So number one step is look for management errors before you look for epidemiological weaknesses, but both of them can be involved, and it can go either way. So finally, at some stage, you're going to be called to account for your disease control program. Did you do a good job? Have you succeeded? What are the strong and weak points in your results? And what, if we're going to continue to fund you in this program, what changes should we make in the program? Very important to, right from the beginning, plan how you're going to answer those questions when they come up, because it's no good getting 6 or 8 years down the track. The minister asks you some really hard questions and you've got no data to answer them. So think about that right from the very beginning. 10 minutes. Well, I'm on the last 2 slides, so that's good. So what are the things we want to evaluate in our outcome? Changes in human cases and human disease, number one priority, but also by far the most difficult thing to measure. Changes in animal prevalence or the number of animal outbreaks. Variation in success between different geographical areas, between different production systems, between different disease control management styles, all of those kinds of things. What changes you made in the program to respond to the emerging issues and what effect those had, and what the overall benefits and costs of the program were, both for human health and animal health, and the expected benefit and costs of doing more. So finally, I've covered 20 years of your work in 45 minutes. A control program is a big undertaking, and I've tried to just bring out the key points of things you need to take into account, give you a template for doing the exercises during the next couple of weeks, and illustrate it by some examples from avian influenza. So it's absolutely essential in any control program that you do a soundly structured planning and evaluation procedure and to enable you to both control the disease and manage the political processes. As someone who has been involved in disease politics at both national and international level, that's actually the toughest thing. Generally we can control the disease, but getting government support, pushing things through the bureaucracy, those are the tough challenges, and we need to ensure we can do that. Collecting the data and organising it is actually not all that difficult, and it's one of the most interesting parts of the disease control program. You can work very hard on the field operations, but seeing the progress and showing why it's progressing, showing where the problems are, analysing the results in this way, this is what makes the disease control program interesting and rewarding. You feel you're getting somewhere. So unfortunately, it's often the weakest link. It's the thing that's not done well. And so a major reason why this particular program has been funded is to ensure we have enough people around Asia who can provide those sorts of skills for the future, because it's really negatively affected avian influenza control in Asia, that we haven't had the answers to the questions. We're nearly 8 years into avian influenza, and we still don't have a long list of crucial questions answered because the proper epidemiology has not been done. So we'll take you through the skills over the next 2 weeks, and you'll start shortly on this first exercise to learn how to do this kind of evaluation. Thank you.
Rogers willing to take on some questions if there are any.
Yep.
So, burning questions for Roger.
No.
I might lead with one, Roger.
Right.
I beat Dr. Expigiani to this. Both you and Ron, to some extent, yesterday talked about the need to almost stage your way into these control programs. In other words, it's a pick-a-winner strategy. Don't solve all the problems up front. Don't intend to solve all the problem up front. Bite off a piece that you can chew, solve the problem, demonstrate some evidence to the policy makers so that the political will falls into your favor.
Yep. It's much easier to persuade people if you can show some success, and you normally also learn a lot from these initial stages. So trying to do everything at once tends to produce organisational chaos. So staging it carefully is a very valuable way of ensuring that you have success.
Yeah, Professor Morris, I think your experience and rich knowledge was reflected in your presentation. I just have a small query. When you said formulate 3 alternative packages to be chosen by the policymakers, if we have just one effective strategy measure, how can we make 3 alternative packages to be offered to them?
Well, I'm just encouraging you to think of alternatives rather than say this is the answer. If you only have one strategy that deserves consideration, and I question whether that's the case for any disease, then you should be thinking about your alternatives in terms of timing and geographical implementation, just what Eric raised a moment ago. So that is one way of thinking about alternatives, but it's very rare that there are not options. And you may think, oh look, this is the answer. Well, then do the analysis, compare that with 1 or 2 other options, and if it comes out the way you expect, great, you've reinforced your initial confidence, but maybe it won't in some cases. And I have to say, my biggest lesson over 40 years of doing this stuff is every time someone tells me it's obvious that, I know they're wrong, right? When I arrived in New Zealand, they told me tuberculosis is spread by possums contaminating the pasture and the cattle eat the pasture, and we can't stop that. It was absolutely and completely wrong, right? But it was the belief that had never been tested. And I could give you 20 examples like this of where people know the answer, unfortunately they're wrong. So I strongly say challenge everything. And every time I've challenged people over disease control programs, we've found that no, it actually isn't that way. And usually it's easier to control a disease than people thought it was. So I don't think it's ever the case there's no choices. Okay? Oh. Just.
I'm Swasti from India. We have understood how you should stage the program in such a way that it continues and get the funding and the political and administrative will from those concerned. But when do you finally call it a day? How do you stop it? We just can't continue. How do we do that?
How do we stop a particular control program? Yes, it's always more difficult to stop than it is to start, and people get in an investment in continuing that particular activity and they don't want to stop it. You have to take a tough line, and again, my advice is to think about this from the beginning and set a date. By this date, we've got to review this control program and either reassess it or abandon it. and New Zealand now does that with all disease control programs. The tuberculosis program gets periods of 5 years, and then it has to be put up for review, and farmers and everyone else can make submissions saying, no, it's a waste of time, or yes, it's a good idea, and detailed analyses are done every 5 years, and the Minister for Agriculture's got to be convinced to go on, or else the program ceases. So it's not a bad way of doing it. I don't know any other country that's yet using that particular system. But it is tough to stop any disease control program, even if you've been highly successful.
Ravindran from India. My question is, most of the slides which you show request a lot of data for creating that evidence, whether it's for prioritization, for this quantification. In a situation where there is an emergency, say for example avian influenza coming to a country for the first time, or any public health emergency of international concern for that matter, you don't have this kind of data. So if you get into this decision making process of how to go about a control program. Thank you.
Yes, I did. I said that I was going to do the endemic disease because it's easier to illustrate the concepts. It's always possible to collect some critical data in the early stages of an emergency. I've been involved in a lot of emergency disease control activities. We use relatively simple things. So, for example, when I showed you the estimated dissemination rate, you can, in the British foot and mouth outbreak in 2001, we were doing that within a day or two of the start of the epidemic and showing the nature of the problems that were going on. And we started modelling, we flew a team to London. Immediately the first outbreak was reported, and so we were modelling within 2 days to predict the outbreaks. So normally what I do in emergency is to define very simple things I'm going to record. And you will normally start with outbreaks and cases, but then you have to define what else you're going to actively go out and collect in order to answer your questions. Are we going to collect virological samples? Your Nipah case study is a very good one, right? Where the outbreak began, exactly what I just said a few moments ago. Everyone said, we know what this is Japanese encephalitis. And so for months that went on with no one collecting the data and people dying of the disease before they finally started to collect some real data to do it. So one of the things I strongly advise in an emergency situation is that you get a small team of people such as yourselves, 3 or 4 people, who don't have to get involved in the day-to-day emergency stuff, but whose job is purely and simply to tell the decision makers what's going on, to analyse, collect the data, do the things, and they're given quite a lot of a power, and they're made directly answerable to the outbreak controller. That's a highly effective system, but those people mustn't get caught up in the day-to-day stuff. They must be allowed to analyse what's going on.
And case in point with pandemic influenza in New Zealand, where we actually had more case data in humans than they realized. In fact, once someone discovered, oh, we've got some data that's getting collected, why don't we have a look at it? The public health people weren't really equipped to manage that data, and in fact brought in the ag people to help them.
Yes, the veterinary epidemiologists were called in to do the analysis because we're so used to dealing with epidemics that we have standard techniques that we just press the button and produce the answers. So some very nice analysis in H1N1 outbreak in New Zealand was done by veterinary epidemiologists called on by the Ministry of Health.
Yeah, and again, the sense was there wasn't much data, but in fact there was. Someone just had to get it and look at it.
Yep, that's exactly true, and that's what I find every emergency. There's a lot more data than people realise if you organise it in an appropriate way and use the specific techniques that are valuable in an emergency.
We're encroaching on our tea time, so Roger will be available throughout the day to ask questions to. But at this point, can we give Roger a hand and thank him for his talk this morning? So, tea break.